Right, good evening. We are now recording another video or another lectures for the course CS2 Data Structures and Algorithm. In this unit, we are going to talk about abstract data type. Sometimes we call it ADT. We will describe what is the difference between abstract data type and a program, right? And in particular, we want to use two ADT stack and queue to as example for us to see what is abstract data type. Okay, so the outline of this lecture cover 3 points. First of all, we did explain what is ADT or abstract data type and compare this with data structures. And we want to understand what is ADT. And then we talk about C++ STL. STL stands for Standard Template Library. And what is the interface? Okay, how do we create interface before we actually implement it to create the ADT? Right, then we said earlier, we are going to look at stack and queue. Right, so abstract data type, if you think about it, is a collection of data plus a set of operations on the data. So you can see that we are just collecting a set of data, and then we identify what are the operations that we can perform on this data. Okay, we are not thinking about how to implement this operation. Okay, we are just saying we have this collection of data, and then we know we have this set of operations that can perform on this data. How to perform or create this operation is someone else's problem. Okay, that is what we call abstract data type. Later, you are going to see it more clearly, and when we compare this with standard template library. Okay, so first of all, we look at data structures. Okay, data structures, maybe let me hide this guy. Right, so what is a data structures? We say that data structures is a construct that can be defined within a programming language to store a collection of data. Right, so you can see straight away, we say the ADT is a collection of data, but the data structures is structures within the language that can be used to store this collection of data. So these two are a little bit different. So try to see the difference between the two. Right, so for example, arrays which are built into C++ are data structures, right? So it's a construct where you have the index to look at the individual item inside the array, and you can access the array, but you can put in the element inside the array and so on, right? So you say that we can also create other data structures. For example, we want to create the data structures, a collection of data to store both the names and salary of a collection of employees. We can actually create the data structures ourselves, right? So we can create a class, employee, and then put inside this class the information that we want to have. Yeah. So in this case, we say that we have a class and the maximum number is actually 500. We declare this constant. So subsequently, we can actually use this to create array or whatever other data structures. And inside there, we have the string name to indicate the name of one employee and then the salary of this employee. And then we have this some methods, right, for us to do some computation, right? So this is actually a data structure. Right, so then we can create an array to store 100 elements, 100 information of 100 employees. But what is an ADT? It represents a collection of data together with a specification of a set of operation, and we call this functional abstraction on the data. Okay, so you can see that we are just collecting all this data together and then specify the set of operation that can perform on this data. It's a specification. It's not the implementation. Okay, later we will use a diagram to explain this. So functional abstraction means the specification indicate what ADT operation do, but does not indicate how to implement them. So that is a difference. Okay, when you are implementing them, you are already writing the program and so on, right? So also it does not specify how the data are to be stored, right? You only know that there's a collection of data. How do you store them inside there? Whether you are using array, whether you are using linked list, it doesn't matter. We do not care, right? So the idea is just a specification. ADT is, okay, all this data, it could be an employee the record, it could be student record, and then the set of operation, it could be insertion, deletion, and so on. Just the specification, how do you insert, how do you delete, but not how to implement it. And that's why this is called functional abstraction. Right, so data structures algorithm is then the how to implement part. So after you have this specification already, later you're going to see that we use an interface to actually represent them. But then when we talk about data structures and algorithm is the part where we talk about how to implement this ADT. Right, so we say that when we want to look at abstract data type is when a program needs data operation that are not directly supported by a language, for example, C++. Okay, we know that C++ support operations such as addition, subtraction, and some other ADT, right? Map, and so on, binary tree, and so on. But if that's the case, then we need to create our own ADT. Okay, to do that, first of all, you design the ADT by carefully specifying the operation, and then you go and implement it. So of course, as we said just now, the ADT only do specification, specifying the operation, but never do it the implementation. So now we talk about before implementation, meaning that if you are the one who is creating this ADT, and then subsequently you want to use this ADT, you have to do the implementation. Okay, so it's easier if we use a diagram to describe this. So a C++ program looks something like this, right? If you do not need any function, any methods provided by the program, the system or C++, we can simply do you can simply do the driver program, right? You can write everything inside here and then compile it, and then you work, and then you will be able to produce a result. But sometimes we know that STL, the standard template library, provide us with a lot of functions that we can use. And if we know how to use those functions, then we can get the driver program, the program itself, to create a, an instance of this STL class, and then use the function or the method inside this class to do it for you, right? So that's why I was telling students all the time, you also go and look at this standard template library of C++ and try to understand all the classes inside there. Okay, so you can look at C++ reference. The reference is actually like an API for standard template library of C++. Look at the classes, look at the methods inside there, and try to understand the classes, understand the method, and know how to use them, so that when needed, you know they are there for you to use. Okay, rather than when you need it, then you go and look at the reference, you'll be too late. Right, so if the program C++ system provide this STL, giving you the operation that you need, then you just use it. Okay, but however, sometimes the standard template library does not provide the functionality that you need. And then if that's the case, we have to create what we call the ADT. So you can see that this ADT that we are creating is actually quite similar to the STL library or the classes. So now the question is this: do you know how the STL implement all the classes, implement all the methods within those classes? We do not know, right? So therefore, the reference is just telling us their classes are giving us all this information, right? All these methods, how to use it, and so on, right? And what are the data that should be operated on. So STL tell us all those things, but STL never tell us how it implement those functions or those classes. Similarly, when we do specification of ADT, we want to create a new ADT because the STL does not provide us with that functionality that we need. We have to create the ADT. So what do you do? ADT, we have to do the specification. And we do that using the .h files, okay, in C++. Later, we will give you some example. Okay, so the ADT is actually talking about this specification, as we said earlier. It will tell user how to use this ADT. What are the methods you have inside there? Maybe sometimes it provide what is a precondition that must be satisfied in order to use this ADT, right? And of course, if you are the one who is also implementing the thing, then you have to implement the operation inside the C++ file, okay? So this is an interface. This is to tell people how to use it without telling people how it is implemented. And then this is a C++ CPP file extension that tell people how to implement the thing, okay, or you yourself implement it. So you can see that if you are clear about this division, if you write your driver program and you do not need any extra functionality, extra method, you just write the statement, a for loop, while loop, and so on, and you can run. But subsequently, if you realize or you actually wanted to do something and you realize that STL provide you with this functionality, then you will create an instance of this STL class and use the method in your program to run it. And then if you realize that what you want to do is not provided by STL, then you can actually create your own ADT, okay, by specifying it and then subsequently implement it. Okay, so then after you implemented this ADT, you will be able to use this ADT in your driver program, and again, just similar to use a class inside the STL library to actually solve the problem for you. So try to understand these things so that when you are creating your program, you know exactly where you are and exactly you know what you are supposed to do, right? Right, so we can actually use one example to explain what is a ADT. Okay, we can use this. Let me Okay, so we just imagine that this water dispenser is an ADT, right? So again, we need to know what are the data that this ADT can operate on and what are the operation, but we do not know how it is implemented because the engineer implementing this water dispenser will have to do the implementation. For us as a user, we only need to know, okay, I need to put water into this dispenser, and then I know that I can push one button to do something to get what I want. But behind those buttons is none of my concern. Okay, and that's why we say that this is a ADT. Okay, so data in this case is water. Operation, you can chill it, make it cold. You can crush the ice. You can get the ice cube. And then there's an indicator to tell us that, okay, there's no more water, so it's empty. So you have to put in more water. So those are the operation. Right. So data structures, the place where you store the data, right? So the water. So you have to actually have structures to actually store the water that are input. Then after that, you can use it to make it to become water, cold water or ice cube and so on. Right, the wall is actually made of steel. In this case, that is a water dispenser, and input is water, and then output is all those things, right? So you say that crushed ice can be made in many ways. We don't care how it is made. Okay, remember abstract data type means we want to know how to use it. We want to know what we can do with all this operation, all those buttons. But how to do it is none of our business, right? So therefore, we are saying that using an ADT is like using a vending machine. Okay, we just need to know the operation that we can perform on the data. Yeah. Right. So a wall of ADT operation hide the data structures from the program that uses it. Okay. So you can see that in this case, this is the wall. This is what we call the wall. Yeah. You hide the data from the program that is using it. Okay, you hide all this data from the program that uses it. And then the wall itself is actually the interface so that the program know how to use the operation and then to process the data, right? So for example, the interface will tell us that we can add value into the data structures. We can remove value from the data structures. We can search for elements inside the data structures, and we can bring them up. So this interface only tell the program, okay, what are the command to call what are the parameter that you have to add. For example, you want to find, you have to provide the parameter, the key to be found, right? So these are the interface given to the program, and the program don't care about how all these program are actually implemented. Okay, the interface tell you exactly how you use the operation, but it never tell you how the operation are implemented, and that is exactly the principle of ADT. Okay, the spirit behind this ADT. Okay, so maybe you are still afraid about this big term called ADT, but in fact, we have been using ADT or the C++, what they call STL. So as we say already, the STL and ADT are actually the same. Right, so we have already see this, like for example, integer, which are the value, and the set of operation that you can perform on in this integer. So this correction of data and also the operation is what we call the ADT. But in this case, we say that this is under the STL, right? Right. So the idea is, do you know how internally C++ perform addition, C++ perform multiplication, and so on? We do not know and we don't care. We just know that if we use this operator plus, we will be able to add two values together. And that is exactly what ADT or STL is doing, right? So we can right, you can type in the operation example minus minus pre-decrement or the what they call division and so on. Okay, Boolean you have all and not, right? So all these operation you can perform with the data, but how they are done we do not know. We don't care. Right, so we say that the standard template library is a powerful set of C++ template classes to provide general purpose classes and function with templates that implement many popular and commonly used algorithm and data structures. For example, vector, list, queue, and stack. They are all provided in C++ in the standard template library. So if you want to know how to use all this, as I say, go and look at the C++ reference, and then they will have description, they will have example for you. And then one of the key benefit of STL is that it provides a way to write generic reusable code that can apply to different data type. Okay, so when we talk about generic, meaning that this class can take in different type of data. Okay, it can be integer, can be character, it can be even a record and so on. As long as when you create the object, you initialize or initialize the data to be of this type. Then the C++ class, all the operation can be performed on this type. Right. So again, look at the reference and see how we can make use of it. Right. So this means that you can write an algorithm once, and then you can use it for different type of data without having to write separate code for each of them. Right. So this is what we call generic. Right, so we mentioned interface that allow the program to or inform the program what are the things that you can do, what are the operations that you can do, and specify what data or what parameter you have to provide in order to use those function and method. Okay, so this is how you specify the usage of all these function or method, right? So we say that this specifying related method, we use interface to do it. Right, so you say interfaces provide a way to specify a common set of operations for possibly unrelated classes and can be used to specify an ADT, right? So when you want to create an ADT, you create an interface first, right? So for example, in this case, so the interface tell you all the function, okay? For example, you can do insert, you can do search, you can do delete, you can do contents, and you can do, look at the size. And then normally you do these comments inside the what you call the interfaces, right? Later we are going to see that we are using the .h file. So all these comments are important. The idea is in this currently, the interface down here did not specify what are the functionality, right? What you want to do is you use these commands to tell people using this interface or this ADT that this method called insert is to insert a key value pair into the table, right? So in this case, most of the time, key is the unique key for you to insert data into the table, right? We have done mentioned that before in hashing and so on, right? So you can see that this interface down here only give you the parameter and the what you call the method name without telling you how this is implemented. How do you insert? How do you search? How do you delete and so on? So this is just telling you how you make use of all these things and what parameter to give and so on. And this is what we call an interface for the user to know exactly what are the functionality that you can actually perform, right? So it said a class is said to implement the interface if it provides all the implementation for all the methods in the interface. So for example, if you want to implement this interface, you must implement all the method inside here. This is given by the interface. That is what it means down here. A class is to implement all the interface or all the method inside the interface. Okay, so example. Normally we use the .head, the header file, to specify the interface. Okay, so we specify the data inside here. What are the data type? And then we specify all the methods without the method body. It's just the method heading, right? So in this case, we say already for this interface, you want to specify, put comments to describe what is the method, how to use it, and so on, without knowing how to implement it. Right? And then this is another interface. Just now that one for list nodes, now is for the list. Yeah. So similarly, you can actually implement the interface without implementing the body of the method. Right? So this specification specify what you can do with a list node. Yeah. Or a linked list. This is list because the previous slide is actually about the list node. Right, then we have to implement it ourselves since you are the one who is creating this ADT. You have to implement it before your main program can use it. And you do the implementation in the CPP file, right? So in this case, you can see that previously this is a constructor for the list node, right? So now you are implementing the constructor by specifying the statement inside this constructor, right? So implement the constructor and implement the rest of the method one by one. Okay, so this is to implement the linked list, okay, CPP. So insert head, we know that to insert to the head, meaning that we have a linked list already, and then we want to insert the new nodes. What must you do, right? So first of all, you have to create the new nodes. All right, so this statement create the new nodes. Then you say new node next point to the head. So before that, head is pointing here, right? Head is pointing here. So you create this new node and this point to the head, meaning that now this is pointing to here. And then what do? You point the head to here. Right, so this is exactly how you implement the insert head operation. And so that's why this is what we call the implementation. Yeah. And similarly, to remove the head, what you do is just pointing the head to the second node. Yeah, and then you are done. Of course, what we do down here, as we say, you have to do housekeeping, yeah, for the increment and the decrement of the size after you insert and delete respectively. Okay, then once you have created the ADT already, then you can actually use the ADT um, to help you to solve the problem inside your interface, inside your program, right? So this is a driver program, so meaning that we have already done the list and then list node then list. Now I want to use this inside here. Using these two inside here to solve some problem, right? So I can actually insert this value inside there. You can actually insert one more. We can actually insert again and so on. So this actually created the list. Okay, so this is inside the driver program. Right, continue with the driver program. You can print out and say, okay, what I'm going to do, and now whatever method that you have to, or the functionality that you want to have inside your program. So basically, we are saying that the number of occurrence of 9 is inside here. So every time you check if it is equal to 9, then you increment the count, and at the end, it's just what you call count, print out the number of elements. Right, so this is like the driver program. Okay, so that is what our understanding of ADT, meaning that it depends on whether you are the one just specifying you might be the team leader. So you specify this ADT so that other team can actually use it. But then maybe you are the programmer. So you will be asked to implement this interface so that the operation or the method inside the interface are implemented so that other people can use it. But they do not know how you implement it. They only need to know the specification, what method to call, what parameter to give, and so on. Yeah. So those are what we call ADT. Right. So now we want to look at two ADTs that help us to do many things. Of course, as we say already in what they call STL, C++ STL, they are already have stack and cube inside that. Okay, but why are we implementing it? Let's look at it at the end of the lecture. Right, so stack is actually a last in, first out data uh, ADT. Okay, uh, inside that the structures actually hold this data. The last element that put into these structures will be the first element to take out if you perform the insert and delete operation. Okay, so let's look at this stack. So you say a stack is a collection of data that is accessed in a last in, first out manner. Okay, there are three major operations. You can push, you can pop, and you can pick. Pick means look at the top elements. Okay, so how these operations are done? So you can push item on top of the stack, right? You can remove item, pop it out from the stack, or you can look at the stack and see what is the value down there. Okay, one of the things that you have to remember, you have only these three operations. Okay, you should never try to check what is in the middle of the stack. This is not allowed. So sometimes we say that this is actually the regulation. Okay, of ADT, you should not violate this property of ADT. If the ADT provide you with only pop it and push, you cannot use any other operation. Okay, otherwise you violated the ADT property, right? Right, so the stack can be used to do what? When you call a function, okay, the idea is you write a main program, and every time the main program call a method, you have to pass control into the methods to run the operation inside the method. And when it is done, you have to go back to the calling program and continue the execution following those the method call. Right, so the idea is how do you send control into the method and be able to come back? They have to store this current state of the world inside the program onto a stack, right? So every time you finish, just pop the top element on the stack and then you continue executing that. Okay, so this is what we call using a stack to actually store the returning address of the function call. And of course, we know that if you need to store the store the returning address for a function call, when you are doing recursion, definitely you need to store all the recursively all the call that you make. Yeah. And then another usage is called matching the parentheses. We will look at this example. And we can also use stack to help us to do uh, evaluation of arithmetic expression. Okay. And we can see how we can do postfix calculation, and we can see how we can convert infix to postfix operation, right? And traversing a maze. Okay, so for example, if you go into the maze, when you come to a junction where you have two possible paths, you will follow one. But the idea is you might hit a deadline and you want to come back to the previous junction. How do you do it? You store this junction onto a stack so that when you want to come back there, you just pop and then you are like teleporting yourself to the junction. Okay, so that is how program work when they are traversing a maze. Right, so let's look at one example of how a stack is used. Right, so first of all, we create an empty stack. Okay, create an empty stack. And then you call the method push, right? You push one item. So let's look at the stack. Create an empty stack. And then the first operation is to push. And then you push a 2, you push a 3, and then you look at the top item, which is equal to 3, and you store it into a variable D. You pop the item, so 3 disappear. You push another 4, and then you pop again. So the 4 just push in, last in, but the first one to go up. So this is stack. Okay, so we can implement the stack using the basic data structures, right? So we can use array to implement a stack, and what we need is just a top index pointer, right? So the index pointer is pointing to the top of the stack, pointing to the element. So if you want to access this element, you just use this top to be the index to go to the elements, and you get the value. Okay, how do we push? So first of all, you have to move your index to the next value or next index, and then you put the value inside there. Okay, and then you go update the size. Okay, and then after that, you want to push 7. So similarly, you move your pointer to the next element, and then put the 7 inside there. Okay, when you pop, you just delete it, and then you have to move your pointer back so that the pointer is always pointing to the top element. Yeah, so basically this is how you make use of stack implemented using an array. Okay, just an index pointer will do. Right, so we can also implement it or creating a new what they call a class, right? So we can do it using two ways. One is using inheritance, but we are not going to talk about this for currently, okay? Otherwise, we just use composition, meaning that we already have the class, and then we use this to create a new class. So class A is making use of B, right? Is class A is composed of the instance of B, making, in this case, we are saying that we have this B class array, class B already, and class B has a lot of all these operations. And what we want to create a class A so that we are going to use all the operation in B to implement the operation that we need for class A. That is what we call composition. Okay, so in this case, let's say we want to do stack implementation using linked list. So we use this basic linked list class to do it. So basically, basic linked list is a linked list where you can only add to the front and you can remove from the front. Okay, you cannot add to the back or remove from the back or add to the middle. Right, so that is a basic linked list. Right, so as I say, we are not going to look at inheritance currently. Right, so we use basic linked list, meaning that we can only use a head pointer to add new elements and to remove elements, just like what we seen earlier, right? So first of all, we create this basic linked list as an instant attribute, instant object, right? And then this will become the class, the stack linked list implementation, okay? Right, so top of the list is a head pointer, okay, pointing to the top. Okay, so then if you want to, okay, go back. If you want to push an element inside there, what you need to do is you just use the basic linked list class method to add head. So you use the method inside the basic linked list class to create the method for your linked list, right? So the linked list is pop, right? You want to push. To push, you call the basic linked list operation add head to add a new value, right? To pop, to remove something from the stack, you use a basic linked list method called remove head to remove the first element. So therefore, you will have this stack implementation using linked list. So let's look at the example of how you can use a stack to do some operation. Right, so this to ensure a pair of bracket, the pairs of brackets are properly matched. Okay, what does it mean? So for example, we have this expression, and we want to check whether the bracket match properly or not, meaning that each different type should have one opening and one closing, right? If this is the case, we say that it's a perfect defined expression. If somehow you have one more opening than closing, or if the pair when they are supposed to match but they are of different type, then you have to provide an error message. Right, so in this case, we can see that all indicated that all the parentheses or all the bracket actually match properly. So this is a well-defined expression. Right, incorrect example. So this one, we have too many closing bracket, right? We have only one opening and then there are two closing. So therefore, this is not correct. Or this one, too many opening, yeah? And then this one does not match. The bracket didn't match when you have a closing, but in front there's no opening, which is mismatched. So these are errors. Okay, so how do you do it? We use this example. First of all, again, you create an empty stack, right? So every time you want to use an ADT or data, you want to create an empty stack first. And then for every character that you read from the expression, you check. If it is opening bracket, you push, okay, onto the stack. If it is closing, you check the top of the stack to see whether they are matching. If yes, you just remove the element from the stack, right? If closed, then if it isn't matched, you want to flag error. Otherwise, you just pop from the stack and then continue to the next character. Right, then if at the end, you finish all the data already, if the stack is not empty, then you have to say there's an error. So the question is, when this happens, what is the problem? Right, what type of error does the last line test for? Okay, why is it that when you finish already, there are some more bracket left inside the stack, meaning that there are too many opening bracket, right? So that should be the answer. Okay, you should understand this. Okay, let's look at one example. So this opening, you push. The next one, okay, so this is just to check for matching of parentheses. So you don't care about all the other uh, characters or all the other input. So you have the second opening, so you push, and then you skip over all the character and you find the third opening, you push, and then you go to the closing bracket. Then you see that the top is also a square bracket, so they match. So you can remove it from the stack. Okay, the next one is closing again. So you check whether the top of the stack is the matching bracket, opening bracket for this closing bracket. They are, so you remove from the stack. The next one is opening, so you push, right? The next one is closing, so you match and remove. And finally, you have a closing bracket or the brace, and then they match, so you remove. So at this moment, you come to the end of the expression, and the stack is empty. So you say that this is a success. Okay, you say that this is a well-defined expression. Right. So if we want to evaluate some expression, arithmetics expression, normally in our mathematics class, we say that we have to worry about one thing called the precedence rules, right? So operators have different priority over one another, as indicated in some table. So we know that, example, multiply and divide has higher priority or higher precedence over addition and subtraction. And then for an operator of the same precedence, multiply and divide, we do it from left to right. So this one we know since your primary school. Yeah. Right. So in computer science, however, we have three kinds of expression. We have the infix expression, we have the postfix expression, and we have a prefix expression. Okay, so how do you define this? You can see that the infix means the operator is between two operands. Prefix means the operator is before the two operands, and postfix naturally is actually behind the two operand. Right, so an infix operator operation can look something like this. Of course, if we do not know the precedent, then we might have to use bracket to indicate the operation that you want to perform first. Right, so okay, so we know multiplication has higher priority. So if we want 2 plus 3 to be performed first, we have to put bracket to indicate this operation should be performed first. Okay, otherwise you want to perform 3 multiplied by 4 first, we can either put bracket or using the precision rules, 3 times 4 would be operated first. But if you convert this to postfix, okay, so we are saying that infix normally has this ambiguity, right? But if you convert it to postfix, then you can see that the operator is always behind the two operands. So if you encounter this operator, you have to take two operands and perform this operation, and then make it to become a new operand. And then you get another operator in front should have two operands, so you just perform this operation. Right. So in this case, later we are going to say that for postfix expression, there is no ambiguity. So therefore, we do not need the precedent rules. And that's what happened in all the computer, all the calculator, right? Most of the time, they will convert the infix operation to or expression to postfix expression before they perform the evaluation. Okay, so you can have this. So meaning that the first operator you encounter is 3. So therefore, you will take the two operands in front and apply multiplication to it, you get 12. And then 2 and 12 will become operands for the plus. Yeah. So that's the first operation, and then the second operation. So again, this has unique interpretation, no ambiguity. So therefore, you do not need precedence rules. Right, so let's look at this example again. So the idea is every time you want to use stack to help you to perform something, create an empty stack first. And normally if the stack is empty, the first thing that you do is you push. Yeah, but then you have to check what are you pushing inside the stack. Do you push what you call uh, the value inside there, or do you push operand inside there, right? So the algorithm down here say if it is an operand, like for example 2, you push it inside, right? And otherwise, if it's an operator, you have to pop two what you call value so that you can perform that operation on these two value. Okay, so 2, put it inside there. 3, you put it inside there. Push 4 inside there. Now you encounter plus, so you have to take out 2 operands and then perform the operation and push the result back to the stack. And then when you encounter the last element, you pop 2 elements again, 2 operands, and then perform the operation and then put the result back inside there. And once the the expression is done, you have already reached the end, the result is inside the stack. Okay, so you can see that stack is quite useful. So we are going to see many more examples when we give you the assignment to do. Yeah. Right, so the next ADT is called queue, and queue is different from stack. The difference is first in, first out. So it's just a normal queue that you see in the canteen, in the bus terminal, in the MRT, where people queue out, right? The first one that arrive first will be the first one to be served. You go to the bank counter, yeah, and so on, yeah? So this is what we call first in, first out data structures. So a queue is again very useful, a lot of application. So a queue is a collection data that is accessed in, first out manner, right? Again, they have 3 operations. Pull means you want to dequeue, okay? Pull means take out things on the queue. Offer is enqueue, to put things inside there. And then pip, again, is look at the first thing in front of the queue, right? So don't ask us why you call it pull and offer. Why not dequeue and enqueue? So these 2 operations is actually what they have inside the STL. You go and look at STL, you will see pull, offer. You will not see the Q and Q. Okay. Right. So the data structure looks something like this. There's a front of the queue. There's a back of the queue. Right. When you offer, yeah, back and front. When you offer, you push and or you enqueue an item to the back of the queue. When you pull, you actually take out item from the front of the queue, right? Pip is to look at the first item in the queue, yeah, so that you know what is the next element that you are supposed to process and so on. Right, so some users, you can imagine that a group of students sending their printout for the printer to print. The printer have to implement certain queue, right? So the one arrive first will be printed, and then the next second one and so on. Right, simulation, a lot of time, some companies, some businesses, they want to simulate the operation that they are performing throughout the whole day. For example, in the bank system, they want to know which are the busy times so that they will put more counter staff to open more counter and so on, right? So they do simulation. Imagine that, okay, at 9 o'clock, how many people will be coming in and so on. So they use this queue to actually do the simulation. And if you want to do breadth-first traversal of graph, we will look at this later on. We have to actually use a queue. So what do you mean by breadth-first traversal? So for example, I have a graph that have 3 children. Okay, breadth-first means I want to process all this first before I go to the next level. So in this case, once you have created, I process this already, you want to put all these 3 into the queue, right? For example, this is 1, 2, 4, 7, or something like that. So you process 1, there are 3 children of 1. So you are going to put 2, 4, 7 inside the queue, so that the next one to come out is actually this guy, right? You won't be able to put this inside there because it's only when you process 7, then you can access this to put it inside the queue. Yeah, so this is what we call the breadth first traversal of the graph. Okay, then we can talk about checking palindrome. Okay, so this is actually it's not really a application for queue. It's actually combining queue and stack together to solve the problem. We will look at the example later on. Right, so again, to illustrate how the operation of queue is working, create an empty queue, right? So you have the front and the back. In this case, you should always know that this is actually a implementation of queue using array. So you have a front index pointer and you have the back index pointer. Yeah. So when you offer, right? So the front pointer is always pointing to the elements, and the back pointer is always pointing to the empty space. Okay, so that is the implementation. So now we offer again. Yeah, you put the B at the back pointer, and then you move the back pointer back one more space. Offer C, right? So that is what happened. And then I want to pip. So the pip A is the first item, so I store it in D. Pull, you take the element out and then move your front pointer to the first element in the queue. Offer, put E inside there, point the pointer back. Pull, remove the first element and point the front pointer to the next element. So this is what we call the operation of queue, right? And how you use it. Okay, so the idea is using array to implement a queue is easy because you just move the front pointer and the back pointer when you are putting element inside there and when you are removing the element, right? So, but there's the problem because when you are always removing and then adding and removing, the front pointer is going to go toward the back, and then there will be some empty space in front, and eventually both of them are going to go to the last element in the array. And at the moment, do you stop the queue and say, oh, I cannot do anymore, or you want to do something else? Okay, so you offer, you put it back. You offer G, you move back. Okay, you pull, you move the A, and then remove it. So sometimes we do not need to physically remove the element. Okay, you just indicate because the front is pointing to the first element, so this element is assumed to be deleted already. Right, so as I said, I was trying to say just now. So eventually, when you move the back and the front pointer toward the end of the array, you are going to find the situation where in front you still have spaces, but behind are all filled up. So what do? Instead of using a linear array, we make it to become a circular array. So meaning that when the front reach the back and the back reach also the back can actually go to the front and point, assuming all these elements empty space in front is actually at the back of the queue, right? So then you have a circular array so that you don't waste the spaces, the memory spaces. So sometimes we say that this is actually recycling the space. Right, so in this case, what we want to do to increase the pointer to the next index and also taking care of wrap around when you reach the back, you just do this. Front equal to front plus one, mode the maximum size. So the idea is you can think about this, like for example, the maximum size is equal to 10, right? Maximum size is equal to 10 because 0 to 9. Okay, so the front, let's say we look at the back pointer first. The back pointer is currently pointing at 7. Okay, so 7 plus 1. Okay, you put it inside there, then you want to move this back pointer to here, 7 plus 1. So it will become 8. And then when you reach 9, so this is 9 plus 1. Or it should be equal to 10, but you will be pointing outside. So in order for us to be able to wrap around to the front, you just mode the maximum size. So 10, so this is 10, right? If you mode 10 down here, 10 mode 10 give you 0. So this indicator will become 0. So you go to the front. Similarly, for the front pointer, it's the same thing. When the front pointer reach the end, you just add 1 and then you mode the maximum size again. The front pointer will automatically wrap around to the front. Okay, so that is how you do this. And remember this usage. Okay, whenever you need to uh, go back to the front of a list or I mean an array, you just make use of this method. Okay, add 1 and then mode the maximum size. You will automatically wrap around to the front when the pointer is actually pointing to the last element already. Okay, but what happened when the front and back point at the same place? How this happened? Okay, let's go back. So the idea is we can add elements G, H. So the pointer will be here. You add element I, the pointer will be here. You add element J. Now, back will be pointing to the front, right? So they are pointing together. Okay, so that is one possibility. The other possibility is this. If you keep deleting from using the front pointer, eventually the front pointer is going to point to here. Okay, after you remove G. So if this is the case, they are pointing to at the same time. They are pointing at the same place. So there are two possible cases, right? So how do we interpret? How do you decide whether it is a first case or it is a second case? Right. So the question is asking you whether it is a full queue, whether it is an empty queue, or whether both or neither of them. So what do you think? C, it can be both A and B, right? It can be either full queue or empty queue. Yeah. So we have a problem identifying which case is this. Right. So that when you encounter this, how do you overcome this ambiguity, or how do you solve this problem? So there are two ways to do it. One is you introduce a size. Okay. When the size is 0, when there are two of them come together, we know that this is empty queue. And when the size is equal to 4, when the two of them come together, we know that this is a full queue. Right. So in this case, we have to add one more variable. But we know that in a queue, there is actually a variable. We can actually make use of this to do it. But there is another solution. We actually use an empty space to indicate, right? So you can never have the two pointer pointing at the same value that is indicating the full queue. So the full queue will be true when b plus 1 is actually equal to the front. Okay, then you have a full queue. So there are two ways to do it. Whichever way you think is more convenient, you do it yourself. Right, so we can also use a tail linked list to implement a queue, right? So tail linked list means we have a head pointer, we also have a tail pointer, right? So this tail pointer pointing to the back of the queue, the head pointer pointing to the front of the queue, right? So if you understand this, then we know that it is very simple. To push or to offer, to enqueue, right? You add a new nodes to the tail. If you want to poll, you just remove the first node and point the pointer to the head pointer to the second node inside the list. Then you get a queue ADT. Very simple. Okay, so we don't use basic linked list because we cannot use a add back of tail linked list. So if you just use a basic linked list, what happens every time you want to add to the tail, you have to start from the front because the basic linked list have only pointer pointing to the front. Then you have to traverse all the way to the back and then add one element, which is very inefficient, right? So therefore, we use a tail linked list. Yeah. Right. So again, we create a tail linked list object and then implement this queue linked list implementation by creating using this object. So that, as we say already, this is composition, right? You compose an object and then make use of the operation inside the object for you to achieve the operation that you want to perform for this queue, right? So this is what we call QLL, a class of linked list implementation of a QADT. Right, so the implementation is quite similar to the stack implementation. Also, you have to just implement the push, the enqueue and dequeue, add element to the tail, and then remove element from the head. So we just want to see how we can use stack and queue together to solve the palindrome problem. So the idea is a string is called a palindrome if you read the same way either from the left or from the right. Right. So some of the well-known palindrome is like, for example, radar, did, elbophobia or something like that. So you can see that I. So you read both ways, they are the same. Non-palindrome data is not, liter is not. Okay. So how do you use stack and queue to check whether a given word is a palindrome? So what you do is you given a string, you use a stack to reverse the order, right? So we know that if you put a string into the a stack and then remove it after everything is inside there, the string will be in it will be in reverse position, right? So input is this. When you put them inside there, the stack will have element the last element will be on top. And at the same time, I will create a queue and just put the input into the queue. So the queue will preserve the order, yeah, because first in, first out. Yeah, so they are in the same order. So now what we are going to do is you make use of the um, pop operation and poll operation for queue to see whether the two elements that come out from these two data structures are the same. If they are the same all the way until the end, it means that they are a palindrome. If somewhere in between the two elements are not the same, then we say that it is not a palindrome. Okay, so check if the two sequence are the same. Right, in summary, we say that we can simply use array or linked list to achieve what we want without creating the stack and queue ADT, right? As we say at the beginning, we can just use the array with the front pointer or top to implement a stack, or front and back pointer to implement a queue. So why are we trying to create a stack ADT? So the idea is using array, you say you move the front pointer. People cannot see immediately that you are trying to implement a stack or a queue. But once you say this is a stack and queue ADT, when you say push, when you say pop, even though you are calling the method inside for the array class, where you move the pointer to the next element to insert and so on, but straight away the name stack and queue will tell you that this operation is to push element on top, and then the queue is to enqueue and dequeue, right? The meaning is very clear. So we emphasize this a lot, meaning you write your program, you should make sure your program is actually self-documentary, and people can actually look at the statement and know exactly what this program is doing, right? So you say that that's why the name immediately let us know what they are supposed to achieve. Yeah, stack push is to push something on top, pop is to pop something on the stack. Okay, so most of the time, stack and queue help us to improve our algorithm and their efficiency. So we will make use of some assignment to let you see how we can use stack and queue to improve the complexity of some problem, right? One of the famous example is the monkey swing problem. Okay, we will look at it as an assignment exercise. Okay, so this come to the end of the lecture. Let's stop recording.